Hi everyone, Dr. Bonner here. We're going to be going over projectiles with a horizontal initial velocity. So in this case, what we're looking at, for example, is if I were to take an object and I were just to push it straight out horizontally, like for example, a ball that's launched horizontally from some height. So if we take a look at this ball after each second, like take a snapshot at each second that it's falling, then it's going to follow this nice parabolic trajectory. So the path of it would follow a parabola. When we analyze this problem, we want to use equations and graph it. What we're going to want to do is use key number one here, which is we're always going to look at it as two separate simultaneous problems. So for example, the x-axis and the y-axis are two separate problems. So we're going to have a blue vertical problem showing its fall, and we're going to have a red horizontal problem showing its motion to the right. So let's first look at the horizontal motion along that red axis. And if we track where it is directly below where it's located, along that red arrow, then we're going to find that it travels some distance delta x in the first second, and then the same distance delta x for each second that it's in the air. This would mean that the speed is going to be the same as whatever it started off with throughout the entire motion through the air. Put short, it's constant horizontal velocity, right? And so the variable for this, because it's along the x-axis, would be, instead of using v naught, we're going to use vx, meaning it's the velocity along the x-axis initially. So in this case, vx naught is equal to v naught, only in this case because it's launched horizontally, right? So we got to be careful of that. We just want to make sure we understand that we could call Vx naught the entire initial velocity. So whatever velocity I push it with, if we launch it with the speed of 5, then that's Vx naught. It's the horizontal velocity of 5 the entire time. Right? That's only in this case because the initial velocity of 5 was directed horizontally. This should make more sense once we look at some examples where it's not the same. So now if we just look at this as being straight line motion, right, we're not even caring about if it's going up or down in this case, right? We're just looking at the fact that it's moving to the right horizontally at a constant speed. This is always true for any projectile because if you look at the forces acting along the horizontal axis, there aren't any, and we're not including air resistance at our level ever. So we always know that any projectile that's flying through the air is always going to have a constant velocity the entire time it's in the air. If we were to track that same logic but look at the vertical motion, then we can get rid of the horizontal, and let's take a look at what's happening here as it falls vertically. So you can see here now, although it's starting from rest, because we didn't launch it up, we didn't launch it down, it was launched horizontally. So that means vertically, it wasn't launched with any initial velocity. The first second, there'd be a little tiny delta y during the first second. During the second second, there would be a bigger delta y, and then a bigger delta y, and then a bigger delta y for each consecutive second after that. This means that the initial velocity at each moment is increasing, which is what gives it that parabolic shape of its trajectory. So vertically, this would indicate, because it's accelerating, right, that we would have an increasing acceleration. And notice here that the variable that we're going to use for the initial velocity along a vertical axis is Vy naught. Vy naught was 0 in this case only because it was launched horizontally. If it was launched upward or downward, then Vy naught would not be 0. So in this case then, we don't really care what's happening vertically. We're just looking at it as like the pumpkin drop, or as me just taking a ball and dropping it as it falls vertically down from rest. This is always true for projectiles because gravity is the only force that's acting, which means that it's accelerating due to that unbalanced gravitational force. This also would mean that that acceleration is 9.8. We found that from the pumpkin drop, so you can reference your notes from the pumpkin drop to show that that acceleration for all objects, no matter how big or small that pumpkin was, for example, had the same acceleration, 9.8. Let's take a look at an example. So there's a seagull that's holding some fish, and it's flying horizontally with a speed of 4.2 meters per second. And it's at an altitude of 3.1 meters when it drops the fish that it was carrying. We want to calculate how far horizontally does it fall along the ground while it's in the air before landing. So the key here is we're going to separate the two axes, and to do that, it's helpful to start to either diagram or list out our givens. If we do a diagram, for example, then my delta x that it travels is what I'm solving for. My v naught is 4.2, and that's horizontal. Vertically, I'll use blue. Delta y is 3.1 meters down. And then the accelerations I know are 0 along the x-axis, and then 9.8, or we can use 10, downward for the vertical acceleration. If we were to list this as a table, it would be the same information, but it's in more of a vertical list here. The tables do lose context, and the biggest issue that we'll have here is that there are arrows in the diagram that indicate the positive and negative sign for our values that may be lost if we just list them out. So you can see here I put little arrows next to these to make sure these all have the same sign. So for example, in the diagram I made down positive. In my list here I made down negative, just to show you it really doesn't matter as long as we're consistent. So if you're not sure, you can always just make down negative and upward positive, or like I did in the diagram here, if you prefer, because all the variables have downward arrows, we can just make them all positive. That would mean that anything up would be negative. As long as you're consistent, you'll get correct answers. So from here, a key obviously is going to be look for hidden quantities. So for example, Vx naught is 4.2, A along the x-axis is 0. That wasn't directly given, right? Vy naught is 0, wasn't directly given. Ay is equal to negative 10 is not directly given. Those are things I was able to infer from the context, or I know are always true for projectiles. The other part of this would be shared quantities. So none of these variables are shared. Delta x and delta y are not the same. The v naught for the x-axis and the y naught are not the same. The acceleration along the x-axis and y-axis are not the same. But time is the same. So time is going to be a very valuable variable to get because the time from the x-axis is the same as the time in the y-axis. So you'll find that we'll oftentimes be solving for time because it can be used on either problem, the x-axis or y-axis. When we use these equations, these are fancy looking version of the equations we have, at least 3 of them. These can be applied along either axis, but not both. Not both. Just it's a red problem or it's a blue problem. So we're just adding double the work here when we have double the dimensions. So when we solve this problem, I have my diagram here, but let's say that I do the x-axis first and I realize that this is an equation that I have, and I'm given, I don't know delta x, I'm given Vx naught, and I don't know time. So that's going to tell me to go to my y-axis because I know time is something I can get from either axis. So when I list out all the variables in my y-axis, trying to solve for time, I can use the same equation but with the y variables, and I can solve that for time, and I get 0.78. Now I can go back to my red horizontal problem with that time, and I can get my final value. Thanks for watching. I hope this makes sense, and we'll do more practice in class.